Good morning, everyone. My name is Saurav Das, I'm VP of Engineering at ONF. I lead the SEBA work, SEBA VOLTHA, and a few other projects. And I'm here. In this session, we'll be talking about, we're going to start talking about the implementation. So I hear in the first session, you've already gotten hands-on with your own SEBA pod. Running in SEBA-in-a-Box. So SEBA-in-a-Box is really a great tool for getting started, and I strongly encourage you to not just be a part of this tutorial and work with it, but when you go back, do try SEBA-in-a-Box of your own and get familiar with the interfaces. So we're going to dive deeper into the implementation in this section, but we wanted to start things off by giving you a taste of what it's like to work in the SEBA community, because without the community, it's really not, all of this work that we have done, all of the implementation wouldn't have been possible. So I'm going to talk a little bit about the SEBA community and the ONF, how it's involved, how it manages teams through brigades. And then Scott is going to come back and talk about the network edge mediator, which is a big section of which is a big piece of software as part of the SEBA pod. And then Matteo will talk about ONOS, which is another big component of a SEBA pod. Okay, so the SEBA and VOLTHA community is very big. It's fundamentally built around ONF and the three operators that are greatly interested in SEBA. That's AT&T, Deutsche Telekom, and Turk Telekom. But then there is a whole bunch of other operators, as well as our supply chain partners and members in the community from all these companies that are part of the SEBA and VOLTHA community. So the question to ask over here is, how do we manage the work? How do we ensure that everyone is rowing in the same direction and making forward progress? Okay? And the way to do that is through brigades. Okay, so what is a brigade? A brigade is a team that comes together for a very specific purpose. Okay? It comes together for a very specific purpose, a set of well-defined tasks, and run that task through to completion. Okay? And there is typically a mentor. It typically is someone from ONF, but as you can see in the very first brigade column, we also have a non-ONF from one of our partner companies, Sienna, David Bainbridge, who's leading that particular brigade. So the idea is there's a mentor, and there is a set of people who have put their hands up to be a part of the brigade, and there is a very well-defined set of tasks that this brigade leads leads that brigade to completion, and then the brigade disbands because that job is done. So this is how we try to organize the community and ensure that everyone is making forward progress. Okay, so we have about 7 active brigades right now in the SEBA and VOLTHA community, and I would like to give you a taste of what these brigades are, what they do, and how you could possibly get involved in any one of these brigades if it interests you. Okay, so I'll start off by talking about a brigade that has actually run its run to completion, and that is the Technology Profile Brigade. Okay, so the idea over here was that you've seen this in the first session, basically about how VOLTHA abstracts the PON, presents a logical switch to the SDN controller, and then how applications are then written on top of the SDN controller to bring out features in the PON. So part of that logical switch abstraction is that a switch should be able to perform QoS. Okay? And so that's where technology profiles and speed profiles come in. So speed profiles are also sometimes called bandwidth profiles. And when we say tech profiles, really we mean technology profiles as well as the bandwidth profiles, because they work together. Okay? So the speed profiles are important because this is where a service provider can do the per subscriber bandwidth allocation, right? So someone has signed up for 50 megabits per second. Somebody has signed up for a gigabit per second. And so how do you shape and manage the traffic so that each subscriber gets what that subscriber has signed up for? That's all handled by the bandwidth profiles, okay? So those bandwidth profiles are fed into ONOS, and you will go through the steps in this tutorial to see how that works. But at the same time, there are a set of requirements that the operator has in the PON in terms of QoS. You know, let's say one operator wants to give more priority to a certain kind of traffic versus other kinds of traffic. Another operator has different scheduling policies. So all of those are managed in the PON. And as you remember, the SDN controller, because of the abstraction that Volta presents, isn't actually aware of these low-level details of how many GEM ports you use or how many TCONs you use or what is your scheduling policy between them. So those things are fed directly into Volta. And the work of the stabilization brigade was to bring these features alive. First, the tech profile features for managing QoS in the PON in Volta, and then the bandwidth profile features on a per subscriber level in ONOS, and have them all work together. So this is something that we do support in the SEBA release and on Volta 1.7. These things are also coming into Volta 2.0 right now. So this was a very successful brigade that lasted the first 6 months of this year to the completion of the SEBA release in July. Another brigade is about the use of Broadcom's BAL software. So as you can see over here, when Volta works with white box OLTs, we typically use this driver and that adapter known as OpenOLT. That is software developed by ONF with the community. So we have now moved on to BAL 3.1 actually. And these are the community members with strong contributions as part of this brigade. We're almost there with the upgrade to BAL 3.1. So again, this is a set of people who have come together in this brigade to try and drive this very specific purpose to completion. Another very interesting aspect of SEBA's pod management involves FCAPS, and as part of FCAPS that comes from Volta, there are a few things that we need to know about the ONU. What is the power levels, or what are the statistics? And those are fetched via Volta and pulled out of the ONU and then reported back onto the Kafka interface. But also, there are things just on a hardware level for example, the OLTs or potentially the switches or the servers that we use, where you can learn a lot about the operational status of these boxes, right? So for example, there's a CPU in here, there's a CPU in here, there's a CPU in there also. And so what is the CPU consumption, or what is the temperature of the fans and the blades and so on inside these boxes? These are operational features that the service provider needs to know at any point of time in its pods. And so here we use Redfish. Redfish is this standard that actually came from the server world and has been adopted in these hardware. And the whole idea behind this is that there is a Redfish agent that is sitting here and feeding that data to an external device, when that external device is either asking for it or has pre-indicated that you stream some data to that external point. So the development of the Redfish importer and then having that imported data being pushed onto the Kafka bus and going through our monitoring infrastructure, which you will hear about in the third section of this tutorial. That is the job of this particular brigade. Staying true with the FCAPS philosophy that that operators are always talking to us about and stressing the importance of. There are, as you know, in the PON, inside a SEBA pod, there are a number of features that are brought alive by applications written on top of ONOS. So as a result, the applications know a lot about the state of the subscribers and the devices in the PON in these applications. So the idea is that these applications will publish that state onto the Kafka bus and again go through our monitoring infrastructure. So this is the job of this particular brigade and the people who are in there who come together to publish that information. Features are also handled in terms of brigade. For example, multicast is not a feature that you will try out in the tutorial today because SEBA does not support it. There is a lot of software that is already in there, but it's not complete. And so will come in a future release of SEBA. But the idea over here is that you have residential subscribers with IPTV service. And so if they are in their houses and they are flipping channels on their set-top boxes, those set-top boxes typically send out IGMP join messages that make their way to the OLT and get trapped up to the SDN controller, which is then completely aware of which subscriber is asking for which channel that is supported by a multicast IPTV stream, and does that IPTV stream already exist inside the SEBA pod, or does it need to be requested? If it does need to be requested, the BNG will make that request. But it is the job of the SDN controller to make sure that that stream is first replicated in the aggregation switch, and then further replicated in the OLT to reach the subscribers that have asked for that particular multicast IPTV stream. So again, that's the job of this brigade, to ensure that that happens all across the SEBA pod. Lastly, I do want to talk about another brigade. This is this important piece of software called BBSim. And the idea behind BBSim is that, look, we have this software stack that we have talked about in a SEBA pod, right? But how do we know that software stack scales? Because as you know, this SEBA pod, at least by design, is supposed to support on a per OLT basis, about 1,000 subscribers per OLT. And at least by design, it was supposed to have 16 such OLTs. So how do we know that the SEBA pod scales, a single SEBA pod scales to 16,000 subscribers? So the idea is, if you were to try and reproduce that scale with physical OLTs and physical ONUs, we just don't have it, right? So this is a simulator that's supposed to simulate the PON working with Volta and the software stack just like it was a physical OLT, okay? Now, note that in SEBA, the data plane traffic goes through hardware, okay? That we don't need to simulate, because that's already in hardware. It happens at hardware speeds. What we need to simulate is the control plane interactions of the OLT and the ONU with Volta and ONOS and NEM, okay? So the idea behind BBSim is that it is a control plane only simulator, but then it should be able to scale. Any one BBSim instance should be able to scale to 1,000 subscribers. And so if you have multiple such BBSim instances hitting this software stack, we should be able to get a very good idea about where are the bottlenecks in our software stack, and then be able to systematically get rid of those bottlenecks, and thereby make this SEBA pod solution more scalable. So the job of the BBSim Brigade is not to worry about the scalability of the pod itself, but to worry about BBSim itself and ensure that BBSim itself scales, right? As a tool to measure scale of the rest of the pod, it itself needs to scale. And so that's the job of that particular brigade. So very, very interesting work. So when you look at that, we organize the community in terms of brigade, but ONF itself does a lot of things, whether it's working with the community, as I said, in terms of the brigades, or working with one of our operator partners, or delivering new features ourselves, worrying about the tooling like BBSim for Volta's and SEBA's stability and scalability, or measuring it, BBSim, SEBA-in-a-Box that you're using right now as part of this tutorial, and also performing QA. These are all ONF team member responsibilities in SEBA and Volta. Okay, so we do have instances where the community comes together and does a demonstration. The last such demonstration we did on a wide scale was at BBWF, Broadband World Forum, in Berlin last year, where we had a number of different OLT vendors as well as ONU vendors that came together and used the first release of SEBA. That's what it physically looked like. at BBWF. We will be at BBWF again this year in 2019. We also have 2 SEBA pods or 2 SEBA demos at ONF Connect. So when you get a chance in the next 3 days, please do visit those demos, very exciting demos. One is, of course, of the standard SEBA release, and the other one is looking a bit more ahead, a bit more advanced SEBA demo, where we have embedded, we have disaggregated the BNG and embedded it inside the SEBA pod. Very exciting work. Do please take a look. So that's 2 examples of how the community comes together and does demos as well. Next, so that's what I wanted to talk about, community, and give you an impression about how many people are involved, who are the operators that are involved. We will talk about these demos throughout the day, especially in the last section where we will introduce that embedded BNG in the advanced SEBA demo that I talked about. We'll also give you an idea about how the operators have plans to take it into production. Again, we'll talk about that in the last section today. But right now, we're going to return to the implementation, and so I'm going to hand over to Scott, who's going to tell you a lot more about the Network Edge Mediator.
Now the NEM, its job, as we alluded to earlier in the first presentation, is to bridge the gap between the operator's systems and the SEBA pod. So the operator may have certain OSS systems that they use. In AT&T, ONAP is one example. And the NEM layer sort of is the top layer of the SEBA pod, which provides a convenient interface for these operators to use to manage pod. The components within the NEM are optional to the extent that not all operators may use all components. So we think there's some mix of maybe some of them are mandatory, but some of them are optional. Maybe an operator has a different way of doing a particular thing, like monitoring or orchestration. You don't have to use the whole NEM. You can pick and choose the parts of it that are important to you. The NEM is where you will find much of our FCAPS infrastructure, so our various monitoring, logging, performance tools will be in there. It's also where you'll find infrastructure services like the message bus, you'll find Kafka, and it's where we do our service abstraction and modeling stuff. So we will be talking about a particular component that we developed at ONF called XOS, and how XOS breaks services into service-specific extensions that allow us to extend the NEM with new functionality, and about how services implement workflows that will implement operator-specific business logic. So you can see here that the SEBA pod, so the NEM is this topmost layer, and it's got these various components inside of it. I'm going to go through a container diagram in a moment, but the NEM is taking various inputs from the operator, such as a description of the OLTs, a whitelist of ONUs, what ONUs are permitted, various subscriber information. And through use of a model-based service definition, it will ingest that information and use that to configure these components below it, such as the ONOS apps, VOLTHA, and other services that are running on the pod. So the NEM is fundamentally a collection of containers. We've kind of split this up a little bit, where you will have the management containers here on the left side of the picture and the monitoring containers on the right side of the picture. So on the left side, there is the northbound management interface. That's where the operator would interface with the pod, and you can talk to it over a variety of interfaces. I have color-coded these. Over here you can see the color codes. Some of the interfaces are Google gRPC. So like this line here is a direct gRPC interface into XOS. Other interfaces use REST. So we can talk REST via something called Chameleon, which is a translator, or we can talk REST to something we call the task engine, which lets you run task recipes on XOS. XOS here is an infrastructure component. It's basically a relational database type thing. We'll be getting into some discussion of the XOS core later. It's connected to a database. In our case, I believe it's Postgres that provides the persistence for stuff that is managed by XOS. Sure, so Chameleon is a translator that translates from gRPC to REST. So its value is in components that don't speak gRPC natively. So one of those is our GUI, which I believe currently uses REST to make its requests to the XOS core. So it's basically for any component that wants to use REST instead of gRPC. Tosca is a sort of a declarative recipe language. It's like a YAML-ish thing. Well, you saw the things that Andy ran. So you make up these recipes. Often you use it for provisioning, and you will describe, this is how I want my services set up, or this is how I want my pod set up. You'll make a Tosca recipe. You'll submit it to the Tosca engine. Now, the gRPC interface, that would be more for dynamic runtime stuff. So as you're adding and deleting subscribers or you're querying state, you will do that over gRPC. So often we see that Tosca is more for provisioning, gRPC is more for runtime dynamic management. Sure. So let's see, I think I described XOS as sort of the database management persistence layer. And then the way we designed it is we want the NEM to be very extensible. So we have divided XOS into this core part, which is very service independent, and then this service specific part down here, which implements these, we call them synchronizers. And each one of these contains service specific logic. So to extend XOS so that it knows how to talk to the fabric, for example, there's a fabric service. To extend XOS so that it knows how to program cross connects through the fabric to connect the OLTs via Volta to the BNG. We have a fabric cross connect service. We have the Volt service, which is managing the virtual OLT abstraction through Volta and ONOS. We have something that does subscribers that encompasses the notion of a subscriber. So all of these synchronizers, they both specify the models and contain a lot of the code that implements the interface between XOS and those particular services. So that's kind of the management pipeline down that side of the page. Over here on this side of the page, we have a lot of the monitoring infrastructure. And for that, we've largely used off-the-shelf open source components. So Grafana and Prometheus are very popular for storing performance metrics and visualizing them. We have an exporter that we have written and the community has been working on improving that takes stuff it finds on Kafka, published by Volta or ONOS, and exports that to Prometheus, where it is aggregated in the database and then visualized in Grafana. For logging, we have Kibana and Elasticsearch, which are very popular open source logging components. And we also have, sort of supporting this whole thing, we have Kafka. I stuck Kafka over here, but didn't really draw any lines to it because it's got lines connecting many different components on this, in the NEM. So Kafka is a general purpose message bus. It's used for everything from getting events into the monitoring components to getting events out of XOS so that XOS can notify the GUI and other things of important developments in the data model. Sure.
Particularly on the right side, could you talk about which of those are straight upstream projects or which ones maybe you've customized within SEBA?
So on the Grafana, Prometheus, and Kibana, Elasticsearch,
Yep.
those are we're pretty much using off-the-shelf components for that. We have configured them, so we've developed our own Helm charts that configure them, but we have not really customized those components in depth, I don't think.
So it's mostly just a Helm chart that's unique to...
Yeah, it's pretty much the Helm chart that knows how to bring this stuff up. The exporter is something we did. It's actually called the Kafka topic exporter, and it listens to the Kafka bus and pushes those things to Prometheus. And we have people from Stairlight who are working on that exporter.
Great, thanks.
Sure. So what exactly does XOS do? So XOS, its job is to take all of this stuff over here and operationalize it to the operator. So this is an old slide, so it doesn't necessarily have the whole pile of stuff we have, but you can kind of imagine there are a lot of various services running inside of the pod. There's ONOS and its various ONOS apps. There's Kubernetes and various VNFs running on Kubernetes. You would also find Volta in here. You've got hardware down here. You've got your servers, your commodity servers, your switches. Volta and its OLTs would be in here. It's kind of take all of that and present a uniform interface to the operator, while at the same time being configurable and extensible. So XOS is intended to be a very dynamic thing, and this diagram kind of churns around. So you can imagine at runtime you decide to add some new services. You might deploy new Helm charts via Helm. Those Helm charts might push new specifications of models to XOS. You might also push in new Tosca recipes to re-provision these new services and send that all via configuration into XOS, where XOS will update its data models and bring all of these services into compliant with what you want the state of your pod to be. So it's very much a management and orchestration type of component. And XOS does this by implementing a data model. So XOS, the data model it exports is not necessarily any particular database, but it is very much in the flavor of a traditional relational database management system. So if you're familiar with things like MySQL or Postgres, it's that sort of thing, and we do actually use Postgres as our back end. We do some extension on top of that. So for example, we have the notion of inheritance, so that the core can supply certain base models and services can inherit and override those models to provide custom variants and custom functionality. So the core does supply a number of service independent models. So we have, for example, a user hierarchy that lets you have a user that can log into the GUI, and we have various security around that, so that when you log into the GUI, it checks your password, it knows what models you can access. There's a whole role-based security model in there. We have the notion of compute resources, network resources. There's a whole bunch of core contributions. So then we have service-specific models, and these will be contributed by the services. So there's kind of three types of service-specific models, and I will work through a very quick example on the next page. But a service will typically have a service model, which is kind of its global configuration. Like, I am the virtual OLT service. Here is the global information about the virtual OLT service. Then there will be these service instance models, and we generally use those anytime that we have to kind of subdivide a service into pieces that are important for some entity. So generally we divide services by subscribers. So you might have the virtual OLT service, but each subscriber does own an ONU inside of the virtual OLT service because the subscriber has an ONU at his house. We will typically take these per subscriber service instances, we'll form them into chains, because the subscriber will actually have a presence throughout the system. He not only has his ONU, he's also got a route through the aggregation switch, for example. And then you'll also find some auxiliary models, which are models that are neither the service nor the service instance, but they're kind of glue that holds the rest of the service together. Now, as an example, and we're not going to work through this in detail, but this is just an example of the kinds of models you'll find in XOS. This is the virtual OLT service. It's present in, it has a sort of a chain of service models that goes across the top here. So you can see that the RCORD service, that is the residential subscriber service, it uses the virtual OLT service because residential subscribers need presence in the OLT. And then the OLT service in turn uses the Fabric Cross Connect service because these OLTs need to be connected to the internet. So that is sort of at the global perspective, but per subscriber, each subscriber has this little piece of this. There is a residential subscriber. He has a point of presence in the Volt service because he uses resources there. And he has a point of presence in the Fabric Cross Connect service because he has that cross connect route that gets him out to the BNG. And then these green models are your auxiliary models. So the virtual OLT service, it needs to know about the inventory of all of these devices that it manages. So it's got models for ONU devices and models for OLT devices. There's an abstraction of a PON network that exists between OLTs and ONUs. And we have ports. So for example, the OLTs have NNI ports and the ONUs have UNI ports. So if you were to look inside of XOS, you would be able to pull out all of these models and see how they were being used in the service. We'll actually look at a couple of them through the GUI. Now this slide is just going to show you a breakdown, not necessarily of the models, but kind of how the information fits together to provide a cohesive picture. So a subscriber is going to have a location associated with it. The subscriber has an ONU, and his ONU is going to be attached to a PON port. We will end up putting those in a whitelist, and I believe we'll walk through the whitelist in a bit. But that is the location. So that validates a subscriber's specific ONU on a specific PON port, not just any ONU and not just attached to any random PON port. A subscriber also has tags. So he has an S tag and a C tag. Those tell how to route his packets through the OLT and through the aggregation switch. That was SEBA 1.0, the first release we had. SEBA 2.0, as Saurav was kind of showing you on some of the Brigade work, we did all of this bandwidth profile and tech profile work. So subscribers became associated with a bandwidth profile, which specified their upstream and downstream bandwidths. And they became associated with a tech profile, which specified their residential, business, et cetera, services that they're able to use. So all of that kind of became involved into this data modeling. And knowing the right places in XOS, you can kind of pull at that information inside of the GUI or from the command line tools. So my understanding is typically, each subscriber will have a C and S tag pair. Different services within a subscriber will have different TCONs and GEM ports. Saurav is the expert on this, and I see he has recently appeared, so he could probably answer your question as to how we subdivide this subscriber traffic into the different per service aspects.
So it depends on the operator, actually. So for example, AT&T wants everything on a single TCON and have multiple GEM ports, and then be able to take different traffic coming with different P-bits on the VLAN tag and have those P-bits be mapped into different GEM ports and then be scheduled through one TCON. But if you look at, say, Deutsche Telekom or Turk Telekom, they usually use multiple TCONs, and then they map different services to different TCONs. So, for example, in Turk Telecom's multicast service is on a different TCON than the regular unicast traffic. Okay, so it's operator dependent, and the tech profiles that we talked about are basically to serve different operator needs according to the particular deployment that operator has. Does that help answer your question? Okay.
Thank you. Do we have any more questions? I think we're about to switch over to more lab work.
Just a couple more on XOS. First of all, you said it's an RDBMS, but is it actually is it just sort of storing all the data in it, or is there a separate data store somewhere along the way?
Yeah, so it is actually backed by Postgres. Okay. So it's kind of a wrapper around Postgres. So I will be giving a talk on Wednesday where I will get into some XOS specifics and how you configure XOS and kind of how it adds value. But basically, XOS allows you to take these sort of specifications for the models, and it will configure the schema in Postgres for you, and it will provide an API, a gRPC-based API that allows you to create, read, update, delete, et cetera, objects within that, and a security layer. So it sort of adds a lot of value on top of your traditional RDBMS.
Got it. And then if there's multiple of these things running up in the world, what is the thought that there's some northbound system that's the master for all these, and it's just sending down the subscriber and topology information that's necessary for that instance?
Yeah, so the operator's OSS system would be on top of this. So one thing we did at one point with AT&T, they implemented an abstract OLT layer, which made the entire pod look like one OLT. And it had like chassis and slots. You'd have to get the AT&T guys to really explain it, but it made it into the right abstraction so that ONAP could understand it, and then ONAP could manage multiple pods. But each operator may have their own way of doing that, of taking multiple pods and managing them from a centralized system.
Got it. Thank you.
I'm sorry. In the picture, I don't understand why XOS can control workflow, because workflow is a kind of business logic, so it's a upper layer than the XOS.
Sure. So these, I don't know if you should think of this. Well, I guess it depends on how you think about it. So yes, workflow is business logic, but it is implemented inside of an XOS synchronizer. So inside of the workflow box down here, what there is logic that watches, each of these synchronizers will watch the XOS data model for changes and be able to enact certain things. So, well, let me illustrate it with one of the other easier services first, then I'll talk about workflow. So the virtual OLT service, for example, would be watching the database model for a time when an administrator disabled an ONU. And it would go and enact that through Volta to disable an ONU. Now, similarly, the workflow driver is watching for all kinds of other events, both events inside of XOS and events external from places like Kafka. And when it sees an event, it will go in and it will make changes to the data model. So these components should not be seen as simply subservient to the data model, but they're also able to aggregate external stimulus in and put it into the data model. So there's both a downward and an upward path through synchronizers. I think we're ready to proceed to some lab work then.